Yeah. That's a walk. It's a 5 minute walk. Is it actually? Yeah. I looked at it This is what it is. Jeez.
Yeah, I came in afterwards, I don't know the mic part worked. But they're general people in the city. Good, how are you? You know?
I was gonna say whenever you're ready. Yeah, just give me a few more minutes-ish. Yeah, and then just turn on the mic. And so if people come now. Yes, I'm not gonna shut. Oh yeah, yeah. So they just pull it over.
Okay, so the first one was a chop. Get my 3 minutes. No one has questions.
You could like. Oh my gosh, I was talking because I want to. I know, and then I saw yours.
Interesting stuff.
I say you're watching. Yeah, you guys look similar. I was thinking, well, I'm not scared of things. Like you have little.
No, they've gone right down.
Yeah. San Antonio.
Is it like the definition of a derivative for magnitude?
Yeah. It was okay.
I didn't know you here.
UTC.
like see how that
He
works.
get walking around in shoes.
I don't know, he decided to take a bike minor.
That's interesting. That's actually.
It was the first time he had to use it for 6 years. So,
So,
it does.
Video.
So, Javi, what's the plan for
Okay, so let's get started. Welcome, everyone. How many of you are here for this lecture series for the first time? Yeah, first time. Very nice. Yeah, so good you can all make it. I'm Jing Liu. I'm the Executive Director of the Michigan Institute for Data and AI in Society. And our organization organizes this seminar series together. And also, the space today is provided by the School of Environment and Sustainability. So, yes, we appreciate their support. And so, I want to give you guys a little bit of introduction of who we are. So Midas has been around for 10 years at the university, and we're a university-wide organization to enable the development of artificial intelligence, AI, and data science methods, and the application of these methods across research fields, and for scientific impact, and also for societal impact. So these days, we really focus a lot on helping people adopt AI in research and doing so in responsible ways. And we also build extensive collaboration with academia, industry, and government in doing so. And so the Data and AI in Society lecture series is relatively new. We've started this only at the beginning of this year. And the reason to start this lecture series is really because AI and also data are playing such a big role in society, and also are transforming society and transforming lives, and in ways we don't really fully understand yet. And so the public, the academia, and also the public really should all be thinking about how we want such technology to transform lives and society, and how we don't want them to do so. And also we all should be at the table to determine what the future should look like. And so this series is open to everyone, so spread word for sure to your friends. And no technical background is needed. And all the speakers will be University of Michigan faculty members who are research pioneers with this technology, but also think deeply about the impact of such technology. And so in the next 3 months, we have 3 speakers coming up. I just want to give everybody a heads up. Barbara McQuaid, talking about AI and misinformation, especially political misinformation. And P. Anandan will talk about AI innovation and the global south. And Moshe Chowdhury will be talking about AI and energy. So for those of you who are at the University of Michigan and who are thinking about using AI, just know that our generative AI tutorial series is starting in October, and this semester we offer 3 sessions. You can find more information on our website. And then our annual Data Science and AI Summit. This again is open to everyone at the university and in the community, November 17th and 18th. And so we're featuring 5 keynote speakers, and who are all really prominent researchers in data science and AI, including for example, I'm not going to go through all 5, but just example, including Andrew Connolly, who is a lead scientist in the Vera Rubin Observatory project, which really literally is the largest astronomy project in history, and Ashley Lawrence, who is the lead, I think, managing director of Microsoft Research. And so these are all open to the public, and we'd like to see all of you there. And so today, the speaker today is Professor Jason Corso, and he's a faculty member in the Department of Robotics and also the Electrical Engineering and Computer Science. He's a prominent researcher in areas related to computer vision, such as how machines understand visual information, and also how computer vision can be applied in various ways, from healthcare to entertainment. He's also the co-founder of a company called Voxel 51, which enables powerful AI systems with visual data. So he has been involved in healthcare research for a long time, and so today his topic is really about AI, robotics, and healthcare. And with that, welcome, Jason.
Thank you, Jing. It's a pleasure to be here. Can you hear it through the mic? Good. All right. So I made a great effort to have as few words on these slides as possible, and as little math as possible. No technical background required, but you also don't have to understand everything. This will be fun, because in computer vision you get to show a lot of pictures, actually, typically. Let me just make sure that this is set up properly. Just give me 1 second here. All right, we're good. All right, so fantastic. It's a pleasure to be here. As Jing said, my name is Jason Corso. I'm in the engineering school here in robotics and ECS. I'm a computer scientist by training, but I've spent more than half of my professional career outside of computer science departments, actually, including in a neurology department, a radiology department, now a robotics department, at various places across the US. And I am also, I left the content out about my startup company, Voxel 51, but if you have questions about that, we can talk about it at the end. It's a data-focused startup company, partially funded by Michigan and a spin out of my lab. We have 55 people now, and we're used by many large Fortune 500 companies to do the type of work that I'll talk about today. So we're a dev tool for AI. I also included my LinkedIn here on the bottom of the slide because I'm getting older now, and I'm increasingly vocal publicly about my views. So I write on LinkedIn often, somewhat happy to be frank and candid. And I'm also in numerous popular newspapers as well. So if you want to follow me or reach out to me, that LinkedIn is probably the best way to find me. So I've been interested in the future of where I could collaborate with computer systems or robotic systems or computationally enabled systems, in a peer-to-peer manner for a really long time. Maybe it was because of this ad from Nintendo in 1985.
Will you be the one to witness the birth of the incredible Nintendo Entertainment System? The one to play with Rob, the extraordinary video robot, batteries not included. He helps you tackle even the toughest challenge.
Some of you may be are old enough to remember that release of Rob. I don't know if you heard the last sentence that was said. He helps you tackle even some of the toughest challenges. Well, he failed so miserably that Nintendo took him off the shelves in, I think, 3 to 4 months. And if you fast forward to today, to 2025, so 40 total years, did do we really have systems that are better, that, that can do the type of things that Rob was supposed to be doing, right? Like collaborative AI-based systems that can really solve problems that are physically grounded in the real world? We're getting there. Certainly made progress, but they're still marred with hallucinations, challenged by data needs, power needs, potentially even policy needs. And I think the potential is really high. And let's see how we can realize it a little more. And I think that potential is especially high in healthcare. Some of you, this is an echocardiogram. If you're going for like diagnostic heart health, you'll see this on the screen.
The right ventricle is too much in the center for LVEF. Can you rotate the probe across the patient's chest to center the septum? Highlighted in blue. Good.
Imagine that was Alexa helping the ultrasound
There is some
technician
interference in the view.
work through the
Let's
process
try to
of
move
getting
up
that
one intercostal
scan.
space. Let me know if you need more explanation to help with that.
Right, so she's walking this tech through the actual procedure so they can get a good enough view for the scan, right? So that's a future. That was a demo. That's not real. I typed the text out and it just made it sound like it was from Alexa. But that's a future that's possible, and it's especially necessary in healthcare where there's a massive shortage of physicians, specialists, especially in rural settings where hospitals are closing at significantly rapid rates. So as Jing mentioned, I've been in healthcare for a while. So I did my postdoc in radiology and neurology. So that was 2005, 2006. Let's begin with some early work we did here at Michigan on cardiac surgical skill analysis. Okay, so the core question that we're looking at here is how can AI be used to assess the technical skills in the complex space of cardiothoracic surgery? This is a collaboration with colleagues at the Michigan Medical School in the Department of Cardiac Surgery. And so like today, when you're trying to understand whether or not an individual is ready to practice this type of procedure, the skill evaluation is actually done peer-to-peer. Humans are watching, experts are watching the junior physicians do their work and rating them. And in fact, there was a study in 2013 that collated a large number of these assessments where surgeons submitted videos of their operations, not different operations, but like one, I don't know exactly what operation was in the study, but one operation, one procedure, and then their peers gave them ratings of how well they were doing. And then, so on this graph here, the horizontal axis will be that surgical skill rating. Lower is worse, higher is better. And then they correlated these with the 2-year complication rates for those same surgeons over the prior 2 years. And as luck would have it, if your peers thought you were less skilled, you had higher complication rates. Direct mapping to outputs in the real world to patients. Okay, it's a linear fit to a somewhat messy curve or a set of data, but it's real. There is actual correlation there, right? Like lower ratings were definitely associated with higher complication rates. But in this contemporary day, expecting to have enough experts around to rate their peers to do it is a lot of labor. It's expensive, it's time consuming, there's variation in those studies as well. So being a technologist myself, we began to ask the question, could we possibly objectively replace those peer-to-peer subjective studies with something like automatic computer vision based hand tracking and then mapping those to outcomes? In fact, our early evidence, so we participating in an NIH-funded project for this. Our early evidence suggested that the types of things those experts look for when they're doing this peer rating, right? Like the economy of motion is one of them. It simply means that an expert surgeon tends to move their hands less than a novice surgeon. Very simple measure. And in fact, correlates pretty strongly with outcomes in that sense. So you can see like the non-suturing hand has a greater economy of motion than the suturing hand in this case. So, but this is not an easy computer vision or AI problem, right? There are numerous challenges. For example, there's often a restricted field of view. In a lot of these surgical settings, the surgeon's actually wearing a head-mounted camera that's looking down into the surgical field. Sometimes there are ceiling-mounted cameras as well, and you have to correlate them. But in this case, you can see it's greatly occluded, right? So these frames are unusable for this objective analysis. There are multiple team members here, right? Which is the actual surgeon you're assessing? Is it the one on the right or the one on the left? In fact, for these open heart surgeries, there are often two surgeons operating together in parallel, and they each have their own helper, their own tech next to them. A lot of hands in the view. But there's also a great variation in appearance, just depending on the environment, the color of the drapery, for example, the lighting changes. All these scenarios are actually quite challenging from a computer vision perspective. Furthermore, there are other challenges, regulatory processes, the actual medical expertise needed to then go and annotate that data so we could use it in a machine learning system. But even most importantly, there's just a very limited amount of data. We've been on this NIH project for 4 years now. It's a collaboration between Michigan, Mayo Clinic, a few other hospitals, and we've been able to secure a little less than 200 cases so far in 4 years, right? There are many more cases that are actually operated on a regular basis, but you have to get consent multiple way given the number of people in here and so on. So it's a big challenge getting enough data. Just a quick technical innovation note that we did. So the standard way of computing this type of hand pose in the computer vision literature is to take a frame at any one time, put it through what's called a network, a pose estimation network, which basically means a highly parameterized model that can transform the input pixels in the video to the output variables that represent the pose of the hand. And then because the data is, it's kind of limited and so on, basically for every frame you get, you just send it through the same pose network and get a pose out of that. Our innovation was to not only compute evidence at every frame, but to also input the prior pose and extend the model to incorporate this sort of temporal consistency between these frames. Now, it seems obvious, but sometimes engineers are slow to adapt, I guess. Basic idea, as I was saying, input the frames through this pose estimation network. That actually generates a heat map, which is essentially like a score for where each joint may be or where there may be a joint. And then we just learn a fusing model that incorporates the past heat map with the current one and then outputs a future heat map, which then is converted into the actual pose. In order to train these models, we need a lot of data. I just told you we can't get that much data. We haven't been able to get that much data. So we went to YouTube, and lo and behold, there's actually a huge amount of surgery data on YouTube. There's a huge amount of every data on YouTube. But I have a hazard sign coming up here. If you are squeamish, everything else will be blurred. If you are squeamish, you should close your eyes until I say so. I just want to show you the variability in this data. And in this case, variability is hard for the annotator, but it's good for the machine learning system. We need that variation because it helps us adapt to all of those challenges that we saw before. Like sometimes we're looking straight on, sometimes it's like rotated 90 degrees, and then the video is split up a little bit, so you have even more hands to go and analyze, right? So very challenging here. Okay, it is okay now to open your eyes if you are squeamish. So let's just go through. I won't show you too many computational or quantitative results. This is not that type of talk. But let's just give you some examples. So the top row here in these two videos is what you would get from the classic temporally conditioned approach. And the bottom one is our method. And you'll notice this ellipse here is highlighting the fact that the pinky finger on this right hand actually goes out of view a few times, and the baseline method just loses it because it's not visible anymore. There's no temporal prior, and that really harms future prediction of the overall motion. And you can just kind of see how that happens. And it's just very noisy as well as it sort of pops in and out. And the same thing happens on the right, although it's not highlighted in a yellow ellipse, with the index finger and the middle finger of the hand on the top. But let's just, so we have this method, we got this data, and then we went and trained a model that can take a video like this and then compute the pose estimates on it, right? So we want to take this example and then go classify the skill level. Is it a medical student? Is it a resident? Is it the attending surgeon? And we're also interested in other facets like the respect for tissue, all right? Are you using too much force? The time in motion, the longer the patient's under, the more risk there is to the patient as well, and so on and so forth. But we will use real data, and we will use a simulated surgical task that was published a few years ago by a different group, just because it was a really good data set and used for other skill assessment analyses. So as far as like converting the raw video into usable features that we can train this skill classifier on, we have a baseline which is really just the pixels, right? Like in contemporary machine learning, you always have to just see what machine learning can learn. Okay, in these cases, there's just not enough data for it to do that well, but we still have that as a baseline. But that's one feature. The actual box is computed as well based on the convex box of the pose that we compute, and then the actual pose estimate. And those features are concatenated together. We compute some summary statistics, don't worry about the details, and then go and learn a model. Now the type of model that we learn it's actually a challenging task, right? So we do know the training level of each of the data samples that we have. But when we directly tried to regress to that training level, it didn't work very well. So we experimented with a method called contrastive learning. Contrastive learning is an objective function that allows you to learn a model that will cluster similar instances together and push dissimilar instances apart. And all it needs to know is same class or opposite class. And it can actually be used with unlabeled data if you can get just those constraints. Right, so you take 2 images or 2 data samples, you map them through your model, and in their embedding space, the feature space, they'll drop somewhere. And then you start to add these attraction and repelling forces when you're learning the model so that additional images of the same or different classes are mapped to different parts of this feature space. Okay, and so we use that same idea in this medical scenario. So like for each, say the top row here is one surgeon, so one skill level, bottom row is another surgeon. So we'll use attraction forces to make sure that those things are grouped together in the feature space, and then repelling forces, all those red arrows, to make sure that the opposite skill levels are in different scenarios. So does this work? So here you can see in the simulated data, top row is novice again, bottom row is expert. On the right side, all we're doing is plotting the centroid of that box and the amount where it moves on the pixel frame. You can clearly, if I had just given you a quiz and just asked you like which one's novice, which one's expert, you all would have gotten that correct just based on the exacting motion. And just imagine like this surgeon standing there 6 hours, 8 hours manipulating with their hands, right? The stamina, the challenge to their physical body is real. And so any reduction in motion is helpful. Quantitatively, we can see like this row here, this RGB frames row. So in the simulated case, does pretty well, about 78% classification accuracy. But when you're learning it with the contrastive methods, we're able to outperform that. And the same thing holds in the real surgical case as well. The motion of the expert is a little bit more pronounced now because it's just a more challenging scenario. Like the actual heart is there. He's working with another surgeon's hands as well. But you can still see there's greater economy of motion. And the numbers also tell a good story. But how many people were in that scene? Was there 1, 2, right? There's 4 people here, including the anesthesiologist. I mean, medicine is not a solo sport, right? Medicine is a team sport. I even told you, like, their hands are kind of like co-interacting, and a lot of the work in medical AI and like for these tasks really just ignores the fact that it's a team sport. And I'm more interested actually in the fact that we have a human doctor, an AI doctor, and then the patient. How can we build a team out of the human and the AI system so that the AI system could potentially guide that human whenever the human's confused, not sure what to do, maybe about to make a mistake? It's possible. Humans are fallible, right? So the rest of the talk will be more about that type of mutually beneficial to the patient and the physician AI system that can help lead to better outcomes. But I have some experience in medicine. You may, I don't know, you may or you may not. So let's take a little hiatus away from medicine for 10 minutes and let's talk about cooking. So cooking has like really bewitched AI, especially the computer vision space. We have dozens upon dozens of data sets with thousands, probably even tens of thousands of hours of video that are finely annotated, all from all in the kitchen, basically. Sometimes it's for object detection, so we'll annotate the different tools that are being used or ingredients that are being used. Sometimes it's for actions. Sometimes it's for the whole process and so on. Cooking, surprisingly, is actually rather a good proxy for different real-world, physically grounded AI tasks, including healthcare. Right? When you're in the kitchen, you're baking, it's messy, there's fluids, well, there's flour. Maybe you wouldn't have flour in healthcare, but there are analogs like, for different things, right? It's perceptually complex. Like the oil in the pan here example, right? Like without actually having a human in the room or some like IoT-enabled frying pan, which I'm not aware exists on Amazon yet. You need a human to go and tell you what how hot it is, or if you drop some water in there, does it sizzle? Things like that, right? Cooking is procedural, goal-oriented. Many tasks have layers, like the nested notion of task structure. Even just certain chopping requires good skill. And importantly, there's a huge amount of ambiguity, semantic ambiguity, right? Season to taste. Use a medium onion. I can't tell you how many times I've been in the grocery store unsure of what a medium onion is, right? It's real, right? So what we want to do is take that chef, put cameras in her kitchen, and have the cameras and whatever other sensors are around inform the AI to guide them through what's there. And this is actually a real experience. This is partially motivated from a real experience that I had. So as you all know, it's cold in Michigan in the wintertime. I do like to cook. In the summertime, actually, summer and winter, I like to grill. But in the winter, I like to cook, like hot dishes, warm dishes, especially on the weekends. And I cook soups, but I had never cooked a chowder before. And so I'm like, dude, I got to try to cook this chowder. And I got very excited. I went to the nice grocery store, I forget the name right now, over on Stadium on the west side. And I got all the ingredients that were listed in the Ski Town cookbook recipe for that. And I got very excited, got to step one, and it said, make a roux. I don't know if you know what a roux is, but I can tell you I did not know what a roux is. And so I was like, what the heck is going on here? Now, so obviously, what did I do? Well, I went to YouTube. I looked up, cooking video examples of roux, and I learned it within 10 to 20 minutes. But the point is that if there wasn't my agent, my helper, my kitchen AI system that could guide me through that, he or she would have been able to show me that video as soon as I looked confused, or I just mumbled, what is a roux? I don't know what that is, right? So that type of guidance and helper is what we're looking at. So in my group, we have used cooking. In fact, we actually do cook in the lab in the Ford Robotics building up on North Campus. No heat involved except microwave. But we're trying to work toward building these types of guidance systems. So I'll show you a video here of an AI agent that we call Millie. And Millie can track so Millie knows what recipe you're doing, and she can track watching you. So there's a camera, I'll show you, there's a camera on a head-mounted display that's being worn in this particular example. So there's video feed coming in, and she just tracks what step you're on. That was the part one. Significantly non-trivial, but we were able to deliver this. So what you're seeing here is the human. I don't know if this might be one of my students who's out in the audience there. In one of we actually use 11 different environments, some apartments, some labs, things like that. What's on the screen here, it will show up very big down here as well as the subtitle, but is the output of Millie, like Millie's state, what she thinks is happening at that moment. For example, it says right now, whisk the batter until no lumps remain. And just this screen here is Millie's brain, or like the debugging interface. The actual recipe that this individual is cooking is something called a mug cake recipe. which is something else I didn't know what was until we were working on this project. Think like a standard like bundt cake or whatever, but in a coffee mug that you can cook in the microwave in less than a minute. So we didn't try to eat any of them in the lab. I don't think any looked that edible when we made them. All right. You know, and so she's doing pretty well, right? She can follow the task. It's playing at like 4 or 5x speed, and with reasonable accuracy for the recipes she knew about and had training data to actually execute with. To actually achieve this, we built a relatively sophisticated AI system. This project was started around 2017, 2018. So we didn't really have the large language models or large vision language models that are available today. Even saying that, though, I don't think we ever would have had enough data with enough consistency to actually like train a repeatable model. So Millie, in her brain, she has a graph that represents all the states of the recipes that she knows about. Each of those nodes is grounded, this term grounding is really critical to this type of work, is grounded in actual perception. Whether or not that perception is visual or audio, or if there are some other IoT things. Again, imagine like a IoT-enabled knife or other cooking supplies. We want to use all the sensors that are available. She is aware of textual recipes, and also there's a mapping in annotations from different recipe steps to different subgraphs, if you will, like realized subgraphs and their video examples. So we made a lot of these mug cakes. We also made a lot of peanut butter and jelly sandwiches and a lot of other things. It's par for the course right now. But a really key problem given this representation is to figure out when and how to actually guide the user. Right? It's non-trivial. Do you use language? Do you use audio? Do you show them a visual example? All of that is still, we're at the very basic frontier. In this particular project, we were using augmented reality through these HoloLens or glasses type displays. We went from a head-mounted camera like called a Mevo to a Microsoft HoloLens. This project is now defunct. Microsoft no longer makes HoloLenses. So we moved to the Roku Air Pro. And there's a new one that just came out a few weeks ago from Meta and Ray-Ban. Looks like a really nice form factor, not much thicker than regular eyeglasses. Maybe that will be better. But ultimately, we had to figure out like what is the right information to show and how do you inform them. But even do more interesting things, right? Task following is not that interesting. It's just it's table stakes. It needs to be there in order to figure out whether or not some other information. Like here, my student Philippos was making a cup of pour-over coffee. That was one of the recipes of interest. And if you notice, the step he's supposed to be doing is measuring cold water. What instead he's doing, if you can see, there are coffee beans falling out of the coffee mug here. He's on step 4. He's weighing the beans too early. Now, one could probably argue if you weigh the beans before you measure the water, it's still going to be coffee. Millie doesn't have that level of experience yet, but that's why this is a great and challenging problem. And then we began to adapt this Millie, or Millie's sister, Tilly, for like battlefield medicine, right? Like, how can we go and do task following from the same type of helmet-mounted augmented reality to track the procedure of different things like a pressure dressing or a chest seal example? This is collaborative work with BBN, a technology company. So you can see there's more variability, but also the motions, the objects are simpler, right? So the complexity changes. But even in this case, we need to get a lot of examples of data to go and do that work. And so we call this general area task guidance and upskilling. And it could be a game changer for medical delivery, especially in rural America. But it's non-trivial. Right? There are multiple facets that make it difficult. For example, user trust, right? Like, how do you actually build a relationship between the physician and the AI system so that they don't turn it off, right? Like, you probably have heard stories where like the newfandangled AI were put into fighter jets or things like that. The pilots turn them off immediately, right? Because as soon as it makes 1 or 2 mistakes, we think, we're humans, we'll turn it off. We want to do it our way. So we need to deliver real human-level dialogue. Humans do expect near perfect correctness. Or at least if you misspeak, if you're a human, you can kind of hear yourself a few seconds later and then you correct yourself often, right? We need that type of real conversational or situated dialogue with attention to detail. I don't know if you know this meme here, but this is from the show called Silicon Valley. It's about a startup company that makes a calorie counter. And so they can map all different foods. Well, their pitch to their VC, their venture capitalist, was we can map all the different foods through a camera phone and we'll make everyone healthier. And then it turns out that they only trained it on hot dogs. And so everything that's not a hot dog is not hot dog. And so, yeah. But they had already raised their VC capital. So, yeah. Be careful if you're an LP and a VC. Another challenge for task guidance and upscaling is the grounded perception. We've already talked about that in detail, so I'll move past this pretty quick. Another challenge is like the real world is not simple, right? We can all agree, like in the healthcare scenario, there are thousands upon thousands of different tasks that happen in the clinic, from basic preparation of a wound, for care, to like LVEF, ejection fraction estimation from ultrasound, like you saw in the motivating example. Medical skills take multiple years for students to learn, and oftentimes that learning is not from reading books or watching videos. It's really from doing the work, either as an apprentice, first observing, then doing it in practice, and it's all grounded in experience. This type of data is just not available to LLMs. It is not web corpora. It is real experience, and it takes time to build. Furthermore, these systems need to be real-time and interactive, right? Like, it's not even so much that the user may get annoyed. That's part of the user trust. Here, if we are slow, if there's latency in delivering an inference, it could actually cause a problem to the patient. There actually could be some, like maybe the physician's about to do something wrong, apply a wrong drug, for example, and the AI system knows that it's the wrong drug just a minute too late or 10 seconds too late. Right? That would be a problem that we want to avoid. So delivering fast, context-appropriate mechanisms by integrating multiple multimodal input streams, sensor streams, is very critical. And we want to do this. So this is a fun AI-generated image in a van, basically, out in the middle of the UP, for example. And then the final hurdle that I think is really important to talk through is, like, we really want to move from coexistence to collaboration. Right? If you think about the surgical skill assessment example from the beginning, that was really coexistence, right? The surgeons did their work, we recorded the videos, we stopped, they stopped, then they were rated by other humans, so humans did work, we stopped, and then after that, they were handed to an AI model to do learning. That's very common in a machine learning scenario. But if you really want to build systems that can interactively, in real time, guide and upskill physicians that are not experts in a certain ultrasound diagnostic task, but they need to be in this moment, we need to have better teaming approaches. But humans are complex, AI is complex, and human AI teams are super complex, right? Furthermore, we are ambiguous, we make mistakes, we get exhausted, and so on. So I'll double click on this one just a little bit, and then we'll get to more about the project. So in machine learning or data science, we call this the oracle assumption, right? There's this general assumption that the data we get from humans, whether or not it's at like training time beforehand, or it's like during inference, you ask a question of a human, they're going to give you the right answer, right? Like, we just assume it's correct. Now there's work understanding noisy inputs and so on, but it's definitely in the shadow of the assumption that all human labels are correct. Imagine this case is an elderly gentleman sitting in his favorite rocking chair, and he wants to have a cup of coffee or a cup of tea, so he goes and asks his home service robot to get his mug, right? Please fetch my orange mug. In the oracle assumption, he's actually describing which mug is his, the orange one. And so this is an instance of a set of problems that are pretty common if you think about things that would happen in human AI teams in the visual world, right? You have an input, X, like the image or the video stream or the audio stream or what have you. You have some other prompt, H, like that's from the human. That's the question, like, get me my mug in this example. And then what we want to learn, or what we're essentially given, is a task model, f of x and h, that outputs y, which is essentially maybe the control coordinates to go pick up the mug, or other tasks and so on. It's very common in computer vision, this type of setup. So single target visual object tracking, visual question answering, or the referring expression comprehension, which is what I just motivated there. But interestingly, if you kind of look deeply at the problem here, you'll notice a really key fallacy that's in this common lore. So the prompt and the fixed input image may be aligned or misaligned with the task model, right? So you have your input image, the prompt is second hydrant. When they're aligned, it outputs like the reasonable object detection. I mean, I would argue maybe why aren't we counting from the back? You never know, right? So, but like, there's just alignment there, correct or incorrect, right? There's alignment between those pieces. But there will also be misaligned cases, right? Here the prompt is left banana. Clearly there's only one left banana in this scene, but the task model doesn't understand that. It sees the background with like some big stuffy that it thinks is also a banana, and it outweighs the actual left banana. And the error here might be basically a bad task model, which I guess in this case it really is. It doesn't really know that. Or it could be an incongruence between the task model and the prompt. Now the classical, so we may ask it for like to get a new answer, to reprompt, i.e. like in this case the human input was deemed ambiguous, so the AI system will ask for another prompt. Give me more. Tell me again. Which doesn't, if you use ChatGPT today, like that never happens now. You're never really asked for more information. Generally, if you tell the AI it was wrong, it's like, oh yeah, I was wrong, and then it goes and gives you another answer, even if it was like factually correct, and it can point to a web page in its source data for it being correct, right? So, importantly, the conventional wisdom though is that a task is solved when the task model can handle all the inputs for it. That is like the world of machine learning. How can we lower our loss function to the minimum point? In this work, this collective work in my group, instead we ask a question like, maybe it's better to just improve the human AI cooperation to solve the task together as a team, rather than trying to always build a bigger and better task model. And so this forces us to take the hazy oracle assumption, which very clearly ignores reality, because the old man is not going to say, please fetch the orange mug. The old man's going to say, get me my mug. And what if this home service robot's new? It doesn't know which mug it is. Maybe it's a visitor. Maybe the guy means the mug he used yesterday. Maybe he has a whole cabinet of mugs, right? So we introduced this notion of a hazy oracle that is able to capture the uncertainty, or needs to capture the uncertainty in the human's response, which I think is integral to building these human AI teams. And so the robot says, I don't know which mug is yours. And then the old man, just like if it was a grandkid or a niece or a nephew, they're going to just, oh, I don't know, Grandpa, whatever. What's my, which one is yours? And the gentleman will then clarify the answer, which is critical. So we have implemented this hazy oracle model in a few different scenarios like that I just described. I won't go through this in detail, but in some sense, this is a very nascent area in the AI space. All right, so now take these 5 challenges for task guidance and map them onto healthcare. So specifically, we're very interested in the challenge of rural healthcare. So what you see here is actually, these are publicly available videos from a group at Penn State that are building a rural mobile clinic. It is powered by, I think this is a Ford F-450, and they took an Econoline, like a camper van, hollowed it out, and they put all the stuff you'd have in a hospital room into the clinic, and they drive it out into farmland in the central PA in this case, and actually do medical procedures. Why is this important? Well, we have a problem, especially in rural America, but in fact, in metro areas there are also shortages of trained physicians. What you see here on the map is, so the darker the green is the more the shortage of trained physicians in that region or that county. There are many very dark green regions, right? Especially in the UP up here, for example. I don't know why it's grayed out in PA, but in the West, tons as well. And I was surprised when I got this data how many metro areas also had a shortage of these, of trained physicians. Comparing today to 10 years ago, someone in rural America has to, on average, travel about 7 times farther to get to the nearest hospital, which is just wild. And you can't see this number. This says 136 closures, full or converted, between 2010 and 2021. That's only in rural settings, right? So it is a problem, a major problem that we need to solve, and we need to be creative about solving it. So we are part of a program funded by ARPA-H called the Paradigm Program. Our project is called Vigil. It's Millie's successor. And the goal of the overall project is to use AI task guidance as a workforce multiplier to increase the efficiency and reach of rural healthcare delivery. We are focusing on things like cardiac health, hence the examples, diabetes care, general trauma care, and so on. It will be studied in future years. We're building out the full technical set of scenarios we saw in the Millie graph, as well as the real systems that need to be delivered. Now, we can't do it all. It's a big program. So we're one of 5 task areas. The text is small, so I'll just explain it. But basically, to build these CDPs, care delivery platforms, there are first basically individuals or teams that are already delivering rural healthcare, like the Penn State group. They're not on Paradigm, but they're already doing it. There's a group called Homeward Health in Michigan, other groups like University of Utah, and so on. The second task area is actually physically building this new mobile clinic. Third task area is doing all the software, like the IoT, electronic health records, and so on for that. Fourth is building a novel, ruggedized, portable CT scanner that will sit in the vehicle and be able to scan when the vehicle is remote. And the fifth is intelligent task guidance, which is our field. So we are clearly the sort of the workforce multiplier part of this program. So the CDP they're not built yet. Program just started last November. But we have a mock one in our lab in the Ford Robotics building. It is built to spec to the TA2 actual CDPs. It's built out of 80/20, kind of like grown-up Tinker Toys. You could think of it like that. But we're using commodity off-the-shelf cameras and sensors like GoPros or the Intel RealSense, a 3D depth sensor. And we're very simple setup: 2 monitors, a table, and yet we can do some pretty interesting things in there. So let's talk about upskilling cardiac diagnostics, right? So how can we have a human AI team in a task guidance scenario broaden the reach for cardiac diagnostic health, right? So very concretely, we're looking at the TTE exam. So this is point of care transthoracic echocardiography. So we're taking an ultrasound probe, we're putting it on the chest, we're getting the reading, and we're ultimately looking for what's called the ejection fraction from the left ventricle. This is like the first thing you'll get if you ever need to go to the cardiologist for general healthcare. There are dozens of possible tests that can be done, but this will be one of the first. Okay, and so our approach to this is to use input TTE video. TTE is one type of view. So we're looking for a view that we can see all 4 chambers of the heart, and that lets us compute this ejection fraction automatically. We'll extract anatomical landmarks of the left ventricle here using a fine-tuned model off the shelf. And then we'll use a stoplight metaphor for whether or not the view is good. So we chose to take this big problem space, and we selected or refined it down to one technical problem. Is the view good enough to compute ejection fraction using a model that can compute ejection fraction? And so red means not good enough. Maybe one of the atria is not invisible. Maybe there's noise or interference. The yellow level, right, it means getting there, right? Like most of the anatomy is correct, but maybe one piece is wrong. Probably could be used for ejection fraction if that's the best you can do. But the green light is when we're ready to go. That would indicate to this novice ultrasound individual in the CDP that they can go, it's good enough, keep it there for a second, we'll compute the ejection fraction from that. And so this is running in real time. in our lab. These photos are from a site visit we had in May. So I'm not I've never held an ultrasound probe, but I was able to compute Yayuan's ejection fraction. He's sitting back there. He's a very healthy kid. And other people were as well. This here is one of the program managers. We had some congressional staffers from various representatives in the state come to the lab, and they, again, first time, hold an ultrasound probe and actually do a live thing like this on a patient. So pretty cool. So just here's some more detailed results, you could say. So you can kind of see when the view gets bad, we're getting the red case. In fact, this is an example where we're going from a good view with an expert, so they know it's a good view, and we're slowly moving it away from good view. Because ultimately, we want more than just red, yellow, green. We want a 3D vector, like you're holding it this way now, you should rotate it 10 degrees clockwise, or you should translate it 2 millimeters, right? These micro adjustments really matter to get a good view. We're not there yet, but we're getting there. And we've also looked at other aspects, right? Like real Hey Siri style scenarios where imagine we have the 3D vectors and still the generalist is just not able to get a green light scan. And they're 4 hours from the nearest expert, and they tried to call them up, tried to get them on the video call, but they're in procedure, they're in the OR, they're not available, right? So we're also looking at developing interactive question answer, like Hey Siri functionality for these medical scenarios. But again, it has to be grounded in what's actually happening, right? The pose of the probe is given to it, the video, the depth as well. And we'll be able to ask questions like, how can I improve this, right? And maybe it will answer, try taking micro adjustments like twisting or slightly rotating the probe to bring the atria into view, for example. This is a little too small, but we already have one trial working where you can ask, what view is this? This is an apical 4-chamber view. Is the lateral wall visible? Yes, it's visible, but the left wall of the ventricle is poorly visualized. So that would indicate to someone with even minimal medical training how they might move the probe to get a better view. Right, so we believe in the program and in the lab that AI upskilling is, especially in medical practice, truly is a workforce multiplier. I think this applies more broadly than just medical or healthcare, but generally it's a great domain to realize the power of an AI collaborator. But it's a huge technical problem. It's a huge societal problem, right? Like, what is the relationship between upskilling on the fly, just-in-time training, and long-term training, long-term learning, right? Like, in order to, we need to understand those relationships. Furthermore, if individual A has driven the CDP for the whole month, and then B takes over in October, the system needs to realize any adaptations it used for the first person need to go away, and we need to start over or load in individual B's, profile, if you will. That notion of personalized AI is part of the frontier. We need to adapt to an evolving healthcare landscape. It's my way of saying there's no way this can go and actually be used in practice now, given laws and liability concerns as well, right? But also other new learnings about how to deliver certain procedures, what are good, what are bad approaches, all important. Furthermore, in rural, I guess the healthcare education varies significantly, both in metro and rural areas. And by the way, as an AI scientist myself, AI is just not there yet. There are many, many gaps in AI, which is exciting because there's a lot of work to do. Here's just an example, right? One thing you might do, if you remember back to the soup example I gave, right? I didn't know what a roux was, so I needed to go to YouTube and look up a 2-minute video how to make a roux. And so using visual examples to train someone on the fly, definitely in domain for this problem. But we recently completed a user study that's in review right now that asked the simple question, does context matter in such just-in-time visual training examples? I.e., if we take an off-the-shelf business-as-usual video from YouTube that does describe what they're supposed to be doing, is that more or less or equally useful as one that is automatically generated by an generative AI system like OpenSora or some other model that can generate video in the actual context, in the lab or in the CDP, right? So this is an in-context example versus a business as usual example. And we tried 4 different tasks, had dozens upon dozens of participants come into the lab. And we looked at first aid cases, like those BBN examples I showed like halfway, 20 slides ago or so, and a couple culinary ones, because we love cooking. It's a great example. And we found actually very concretely that the quality of the work improves significantly, 13%, 12%, 14%, 6%, and the time to compute the task drops significantly for using in-context video versus using business as usual, off-the-shelf YouTube videos. The level of increase in performance was a big surprise to us, in fact. Because humans are smart, right? Like I learned how to make a roux. That soup was really good. It was not in my kitchen, that video, right? Like it's natural, but in fact, this does reduce the cognitive load. They can do their on task more effectively. And so we wanted to try, does this work, right? Like can we actually use contemporary generative AI methods? These 4 examples on the right are very recent, state-of-the-art. I think it was WAN 2.2. It's like less than a month old, this method. So what we give it is an input context frame, right? So this is something like the inside of the CDP or something like that. And the text that describes what step we're on in the procedure, right? Apply tourniquet, pull the remaining strap over the windlass keeper, and then go. I'll show you the video of a human doing it. Very simple procedure, not much motion. I can do it again, but only by going back. So, very simple procedure. You would think it's natural to do. A side note: we have this is a real human. He's wearing blue gloves just to avoid bias in the user study. So everyone there, when the participants go and do the work on their own, they actually wear the same clothing. We give them the blue gloves, we give them the army jacket, so that is truly in context. And then I'll show you the examples from the generative cases. So Sora completely changes the context, like it changes the viewpoint. WAN stretches and destroys the tourniquet. Really just the notion of understanding the physical world is not there for these systems, but it gets better. This one's an even better example. Pressure dressing, apply the direct hand pressure at the wound. I'll show the human doing it. Very simple knee, right? The blue cross tape is the wound area. And now let's see what happens here. We are very creative. We actually have the mannequin applying pressure to its own arm. Like, I have to say, these AI models never cease to amaze me. But you might say, wait a second, this is a trick. You're not being fair. There's not that much of this type of data out there. So we should use cooking data or other examples where there's just tens of thousands of data, of examples. And so each row is a different example. Pick up and crack an egg, roll the dough, knit the fabric. These models are a little bit older. This is a little bit older work, but still there are major challenges, right? Just complete physics, loss of physics in practical realities. So there's a lot of work to do to realize this future, but I do think the benefit outweighs the cost. And I think to realize AI's upscaling potential, I think it's paramount or imperative that we bring humans and AI together into collaborative teams with equal footing. I'm sure you are familiar with the classical quote from Theodore Roosevelt, the man in the arena quote, right? Like, critics can be one thing, but really it's the people who are actually doing the work that matter. And I think we can have a new analog in AI for AI's impact that has some notion of putting the human AI team in the arena, grounded in reality, grounded in practice. That's what the arena is, right? Like we actually are doing the work together, learning from each other, learning from the physical experience. That just simply cannot be learned from web corpora. Data out there is not tied to your biomechanics, to the robot's biomechanics or the AI's biomechanics, and so it's lost. And I think we really need to think about the practical implications of that. So before I end, I just want to note that this work was funded by a variety of sources, ARPA-H, DARPA, NIH, AFOSR, NSF. The views are mine, not the government's, but we would not be able to do this work without federal funding, so I'm very glad that we have the funding. Thank you for your attention, and happy to take any questions or discussion.
You mentioned that one of the problems is getting enough cases and getting the consent of people doing the cardiac surgery. Was that consent, patient consent, surgeon consent, hospital consent?
All of the above. Yeah, that's part of the challenge. Certainly patient consent, but also since we want to use the physician data for learning, basically. Usually that data would only be saved for a year or 2 years and then thrown away. But we need to get everyone's consent. Yeah. And in fact, we have an active project now in the lab that is taking all of those roughly 200 8-hour videos. So each case has 2 video streams. One is the head-mounted stream, and one is more that room view. And we are anonymizing it all. So any identifiable features like a logo, a face, surgeons wear skull caps. Sometimes they have embroidery in them, so they're anything that's identifiable, even like the computer interfaces, we're blurring out so that we can release, as far as I know, the first open domain, open heart surgery data set.
So even though nobody can tell who's doing the surgery, they won't give consent?
Well, no, it just takes time and takes, it's just a slow process, basically, yeah.
Thank you very much, Professor Corso. My name is Taufik. I'm a physician by training and currently a first-year PhD in the Hills program in the medical school. So I do some of this work. I was particularly interested in the contrastive learning projects for the cardiac surgery. And for us in the medical school, usually we bother about computational resources and computing power to train these models. I was just curious, what computing power did it take to train some of these models?
Good question. So I'll just repeat it because I think that mic is off, by the way. The question is basically, these models take a lot of power, energy, and GPU cores or computing cores to train. They definitely do. And again, without federal funding to buy that, we would not be able to do that work. But so we generally train most of these models on a GPU node that has 8 H100s in it. So this is a node that cost about as much as my first house, like 220 grand or something like that. But it's still running, and we bought it 2 years ago now. But that's one node, right? Like, if we were doing this in a corporate environment, we would have probably 1,000 of those nodes to do the work. And so, like, our ability to train these models is bound not only by the available data, but by the available compute that could then go and consume that data properly. But then another question is, which I think is relevant, is how do you do it? What computing do you need in the CDP, like at the edge, to deliver these inferences on the fly? So, and I would love to say we only need a cell phone, or like we only need a simple laptop or a tablet, but that would be lying. So we are currently speccing out our design spec basically is a system with 4 GPUs in it. And I can roughly tell you, like, so one of the GPUs will be running, so there's like the agent that's deciding and tracking like what's happening now, will respond, like is listening in on the conversation between the patient and the physician. And if there's ever something like, okay, let's get ready for the ultrasound, then the agent has to recognize that they're moving from state 1 to state 2, for example, right? So that's one LLM running on that. Another LLM is running for the VQA system that I mentioned. Those are 2 different models because that one needs physical grounding, so it's a VLM, not just an LLM. But we also, I didn't mention it here, but we also automate a medical report for the physician, so that when they're done with the visit, they'll have a draft physically grounded report that has images and examples and stuff like that that they can go edit. So that's the second GPU node. Third one runs, I didn't really talk about it here, but we have a full 3D model that represents like the inside of the CDP, so the table, the patient's body, and we can use that model to guide how we generate the interface. either on one of the screens, or we use a projector as well to project like guidance directly on the patient for the physician. The fourth GPU is just an extra for what, just in case something else comes along that we need it for. Yeah.
Thanks for the talk. For intelligent task guidance, do you ever incorporate eye tracking?
So far we haven't. For that study that was like the video context study that I mentioned right at the end, we had debated pro and con for encumbering the participant with an eye tracker. For that study, we decided against it just because we wanted them to kind of be like unencumbered. So we haven't yet. I think there's a lot of value in all these like nuanced features, right? Like the expression, the comfort level. You can read a lot when you're situated with someone. So I think it's it's greenfield. So I look forward to doing more work with it. Yeah.
Hi, Jason. Thank you so much for a fantastic talk. It's very interesting to see the video generation results. I also noticed like you are showing the example on the short video sleep. So which means like the real video you are showing is pretty long, right? So how do you think we can overcome this kind of gap for generating the long video like in the real world? I know what you mentioned is to be more informed about the physical world. But I also wonder, like, what's your insight, like, if we can really generate those kind of video, like the real world video we have?
Yeah, those are great questions, Lee. So there are like I think three pieces there. Like the middle piece you asked about is like when you're listening to the media and you hear about various folks saying world model, world model, world model. Ultimately, they mean fixes to that problem. Mm-hmm. We're just not like but the current approach is don't learn to extract physical principles and then learn how to put them in. We don't have mechanisms for that. It's just get a lot of data and try to use the parameterization to learn them. I don't think that's the right answer. I think the right answer is in smaller models that know about actual principles, but we can't put them in manually. We need to have the system to learn how to discover them. So I think that was one question. As far as like long videos, I like the research community because we can abstract problems away from reality, then make some progress, and then figure out how far away from the new reality we are. Yeah. Right? Like when I one of the first papers I wrote on video understanding was in 2012. It was a basic like input a video, output a classification of what action was in the video. Pretty simple. The videos were like 10 to 20 seconds long, right? So very short clips of videos. That was almost 15 years ago now. Like today, the longest videos people deal with are not much longer than that still for training, right? We just haven't developed the computational and like modeling machinery to really handle long videos. In fact, it's frankly embarrassing. Most of the best performing methods in like video understanding and video generation don't actually use for like the notion of like a video volume. They generally use extracted frames. That was why that conditional pose estimation thing in the beginning, we could even publish that in 2022, right? Like because most methods that are trying to extract and do recognition or understanding from video still just do it on a few frames or frames independently. So there's a lot of work to be done there.
Yeah, for sure. Thank you so much.
Yep.
And also just a quick follow-up at that. So I know like you have shown like the different modalities in the big picture with the VAN, like even go beyond the vision and also the language. So if we want to integrate those kind of the real multimodalities that will happen in this VAN, so how do you think we can do that regarding for the current like contrastive or maybe other approaches?
Yeah, I mean, if I knew, I would probably submit it to CVPR in a month or two. But I mean, it's hard to say, right? Like these days, we do think about tokenization as like a main computational mechanism, right? So like input sensor data or input data of some form or another, and then drop that into some very high dimensional token space. Like high dimensional here means like 10,000, 40,000, right? Like, okay. That space is non-modal, it's like amodal in the sense that like one can take language data, one can take image data, one can take sound data or other sensor IoT data and learn how to map it into one space with something like contrastive learning. I do believe in that approach. I think it's the right approach. The problem is that 40K is too high dimensions. So like we really need to figure out what are the structures in that space to that like the real things that can happen in the real world actually live on. You know, like, because for example, that 40,000 dimension space might be like beer foam, right? Like you pour a pint of glass, pour a pint of beer into a pint glass, and like, you know, you get beer liquid for like 80% of it, and the top 20% of it looks like it's full, and if you pour too much, it'll go over, but it's mostly air. You know, there's like these really fine structures of bubbles in there. So I think we need to do more modeling in this space. Yeah. Yep.
Hi, I just wanted to ask a little less technical question, maybe a little more abstract. So I think something a lot of people might think about this is what happens when these AI systems are wrong. And I think to go a little bit deeper into that, maybe what does it mean for one of these systems to be wrong and the human in the loop also to be wrong? Where does, you know, who falls responsible if mistakes happen that ultimately hurt someone or, you know, worsen their livelihood? And, you know, if you don't know about this is okay, but like, how do you think existing legislation might be able to evolve to potentially cover these kind of scenarios in a way that is fair for patients?
Yes, not a lawyer, don't know too much about policy. However, I mean, there isn't actually much policy out there yet for AI at large, right? So it is kind of greenfield, and we should be having conversations about where should liability stand, where, you know, where things like that. But I think getting back to the first part of the question, I think, so today, again, like I think status quo is, here are the facts. Humans make mistakes. AIs make mistakes. Like these are given, and I hate to say AIs, but like these types of like large language model things, they're just next token predictors, right? Like generally, both can be wrong. We don't actually appreciate the fact that the human can be wrong today in the way we interact and team up between human and AI, and I think that's a big challenge. So what I'm advocating for is that we at least incorporate that type of mutual understanding. That like uncertainty can be modeled bidirectionally. When we get to bidirectional uncertainty, then we should probably think through other guardrail type approaches that will be able to automatically even detect some notion of, wait a second, this is going awry without any domain knowledge, right? So like some general notion of that level of uncertainty. Maybe that's a holy grail, I don't know. In this particular program though, you know, we expect that the human, even if they're wrong, like the humans needs to be trained and taught about those types of guardrails, right? So I would probably argue in this case that generalist, the liability will still fall with the generalist because in the end, they are the one interacting with the patient. And if they're uncertain and they're not getting the right guidance, they need to stop and then go and, you know, call the physician or pause and come back the next day or whatever. You know, and even like on our displays, we have 2 displays. There will be a warning sign at the bottom of one. You know, in the event of any emergency, stop and, you know, call 911 or call for help. Even though we're just in a lab or practice setting, just to capture the notion that like the human is the one that is like leading the way in that sense. Yeah, but it's a good point. Yeah, I think we need social conversations around that. Yeah.
Yeah. So my question is like for a time frame on this, even sort of like just implementing it, and then do you think in the near future we will have like AI not just like implementing it but being like the sole ones, whether that's in like kind of just surveying, or if it's more like actually doing different surgeries, if that's like stitches or like an appendectomy, something like that?
Well, yeah, good question. So I'll take the second part first. So even in the program, so right, there are diagnostic procedures, which we're doing now, and then there are interventions, I guess, or like things that will actually interact with the patient. I do think the program at large wants to get to some minor interventions, like a peripheral drug application. or other venous access type scenarios. We avoided that. Like actually, we've been on contract now about 10 months, and we spent the first, I would say, 5 or 6 months just figuring out what are the clinical services we should focus on, so that it's tractable and like we can study it and use it. So it's really hard to give like a horizon. You know, I'd be I don't know. I don't want to make the same mistake Elon Musk made about that. Yeah, but hopefully in my lifetime.
Hi. I think your second nodule was patient physician reporting. You were talking about that.
Mm-hmm.
Will the video and the transcript, like a provider's notes, be available to the patient in their medical record? And will they have the video and any discrepancies?
I think it's hard to answer definitively, but that third task area, TA3, they're really the EHR czar. And so the intention of this whole system is that everything that's done, especially, well, the report especially with the video, any images or video, would become part of the actual medical record. It's unclear if the video would also be. That hasn't been discussed yet, but it's a good point. Right? Why wouldn't the patient want that as well? Yeah.
Thank you very much. My name is Ajid, and my question is, another aspect of surgical performance is about non-technical skills like communication and teamwork in the operating room. And the assessment of the communication skills relies on humans observing surgeons in the operating room. So I'm curious to learn how far is AI to be able to automatically assess surgeons' communication skills in daily life?
Yeah, it's a very timely question. So in the cardiac surgery case that I showed in the beginning of the talk, I removed all of the non-technical assessments. So that's the general term for, I think, what you're saying, right? Like, for example, when the technician's giving the scalpel or the scissors or whatever to, sorry, they're not scissors in medical practice, they're some tool to the surgeon, if they hand it this way or that way, it can be a problem, right? Like if the surgeon has to pause their work to fix the tool, it slows things down, leads to worse outcomes, and that's demonstrated with existing data. So we're studying it, but there's really no results to kind of report at the moment. We do have a paper in review right now, which is kind of like what is the status quo of AI methods for all facets of medicine, and that type of like even nonverbal communication and non-technical skills are part of that. It's a little bit more of an opinion piece than a technical piece, but that's why I call it timely. Like it's something in top of mind. Yeah. Yes.
So I've been looking at the surgical team, and at some point you have to break things down to some fundamentals. So I began to look at the instrument and try to model it in a toy model. And I was trying to apply Shannon's information entropy to the problem. It's been done a lot in construction and assembly, or operations department, etc. But I'd always struggled with the animate, inanimate interface. And the statistics, the biostatistics between the two are extremely different on their face. But there's almost no understanding of the wetware and its computational mechanisms, the idea of tokenization, etc., are all metaphors that may or may not apply.
Right.
I accidentally watched Sam Altman just being in a conversation with David Deutsch that was taken in the last week, and he's insisting that we're absolutely a million miles away from an AGI, which he determines as a human intelligence, completely different in that it's able to explain things. And when we think of explaining things, I like to use the word grasp. So our minds in some way grasp things. so do our hands, which is more of a physical thing. And so I created a model of a die, a cubic die, they're not all cubic, and came to find that there were an extremely complex probability distribution of the various dimensional ways you could orient that. And interesting, some of them are chiral, depending on what you look at, which is rarely ever considered. And so we put together a study and video, these die being assembled in a very simple manner, but I had preconceived what the entropy was from the beginning state and set up 4 different relative entropy setups. And what I ended up finding was that there was a massive skew of the human performance distributions, but that the physics of the inanimate object is extremely Gaussian. It's just like normal curves, very easy to talk about that physics, and even our hardware can't yet understand the physics of like Newtonian mechanics very well on the fly, let alone how you're going to explain to a human what to do about that. So what are you doing to explore those dilemmas?
So let me, I mean, it's a great point in the sense that, let me summarize what I understood you said it. So it seems to you that many physical phenomena, if you observe them and then compute summary statistics on them, those summary statistics tend to be very well behaved, Gaussian, simple distributions, and that's generally natural. Like that's what we see. But the challenge is that in the instance, like for one case, right? That is still a 40,000 dimension quantity, right? Even like the hand, right? The hand grasping the die and rolling the die or whatever, and if it's a 6-sided versus 10-sided or 20-sided die, like huge variation. So I think the challenge is that much of contemporary machine learning, deep learning, is almost uncomfortable thinking about how to model that distribution. I don't see much work in what is the statistical distribution of human pose or whatever in high dimensions, because I don't think we have the machinery yet for it. I mean, entropy, like you need to have like relatively manageable analytical distribution for it. So I think we want to get to there, right? We even just in my lab meeting this afternoon, we were talking about what are the mechanisms for understanding that VQA work, right? Like in the VQA work, it's not physical, but like a question, the visual input as well. These live in very high dimensional spaces. Is it possible that we can develop a mathematical, like a manifold of where they live in that space? So then on that manifold, we can compute distributions. That's how we're looking at it, but I'm sure other people are trying other things as well. Yeah.
Hi. I realize this might not align directly to the task, but have you considered looking at patients' electronic health record or doctor's notes, just information about the patient specifically?
Could you elaborate, like for what purpose?
Like in the videos where you had all the different surgeries, looking at for each patient. I mean, data's probably not there, but what is their history, and see if that would help some of these methods.
Yeah, we haven't. I mean, it's a good point, right? Like general context ultimately, like could help reduce the dimensionality in some ways. If we know the patient's older than 40, younger than 40, older than 60, younger than 60, like that kind of thing. We haven't done it in this work though, but it's a good point. It's plausible. Yeah.
Hi. Thank you for this very inspirational talk. I actually have 3 questions, hopefully quick ones. The first is that within this whole kind of field of AI upskilling medical practice, where's all the gaps and challenges? Is there any kind of niche areas or applications that has been identified as semi or kind of closer to production ready or implementation ready? If so, do you mind sharing a little bit of that? The second is from. Yeah.
Should we do one at a time? Okay. So the question is, if you didn't hear, like, what are the low-hanging fruit? Is a way of saying that challenges in this type of upskilling, medical upskilling. So, I mean, the examples I showed, like, you know, ultrasound in the heart, or another example is like looking for vein blockages, whatever those are called, I forget right now, like in the lower limb when you have blood clots, right? If you're like a diabetes patient or something like that, you're more at risk. So we chose those examples because we think those are the low-hanging fruit, in fact. And there are some ultrasound probe vendors that are trying to work in some like guidance like we have, like we are as well. So it is a little bit like, I think that is going to be released within the next 5 years, if not already. I mean, I think they are a little bit different in the sense that ours is interactive and physically grounded, and most of the ones that are available even today are not really physically enabled or physically enriched. So that's one thing. There are also companies that are generating automatic medical summaries of what happened, but it's only language based, not physically grounded as well. I mean, the real thing is our like competitive edge is that we model things as physically grounded, and I think that will help drive the problem space. Yeah.
I see. Thank you. Well, the second one is, have you seen a pattern of like roughly how many hours of in-context video will enable the model to get trained and produce a desirable or acceptable outcome in terms of consistency and accuracy?
Yeah, it's hard. There's no one answer. I think because we don't have great models of the distributions in these high-dimensional spaces, we generally observe that more data tends to lead to more consistent outputs of the model. But obviously, if you have some very simple task, you know, I don't know what it is, like stacking one cup on top of another cup, whatever. There are only so many ways you can do that, right? The manifold is smaller. But we really haven't, without such a analytical or sort of like mathematical understanding of the space, we can't get there. But that's one of the hardest problems in data science, right? Like what is the P of X? Like what is the distribution? And I think if we see any like, you know, Fields medal or Turing medal or whatever in the next 20 to 50 years, it's going to be around that, I think. Yeah.
Thank you. The last one is, so you mentioned the constraint of like the comparison between the resources the corporate world has versus academia. Then coming from academia's point of view, what do you think is the distinguished value that the related research in academia brings to the whole field?
Are we still being recorded here? I mean, so in academia, we have the responsibility and the freedom to care about the end user in a way that corporations may not need to, right? They're there. I mean, there is this notion from a fantastic investor named David Gardner called conscious capitalism. You know, the notion that like companies are there for more than just the shareholder, right? They are there to consciously approach society in a great way. It remains to be seen if many companies act like that. In academia, not only can we act like that, we must act like, we have like that responsibility to do that. So, I mean, this type of work is really could only be done in academia or a research lab that, you know, kind of like old classic Bell labs where you don't have to worry about the end game, right? Like, and I think that's where, you know, we don't need thousands of GPUs to do this type of work. Like we're doing user studies, but we're mapping that to actual AI and actual technology. So I think it takes time and effort to like find the right bridge, but it's doable. Yeah. Thank you. Yep. Yep.
So hi, we are one of Morley students, and we're also working on this project on rural healthcare, and how can we leverage like AI systems to help places with more like with places with limited medical resources. So my question is how. What do you think about how we can leverage this system and distribute it and scale it to places where you can make use of the like AI system on like that you mentioned earlier, and then apply it effectively on places where it's more resources constrained?
Great point. The question is roughly like, nice idea, but how do we do it in practice? How do we scale it in practice in some sense? So in fact, one of the early motivations for this work was in the emergency scenario, not the, like, in all this work, these are planned visits, not emergency visits. And so, you know the patient record, you can prepare for it and train for it. My original goal in writing this proposal initially was the following scenario. Imagine you are driving, in rural America. You come to a T-junction between two roads, and at that T-junction you find a massive car accident, right? Like bodies thrown everywhere, cars smoking, like, terrible scene. You're not a medically trained individual. What do you do, right? So the goal was going to be like, well, you take out your phone and you like actually scan the scene, and that agent in the phone then guides you what to do next, right? And obviously in that type of scenario, one would need some connectivity to do the processing in the cloud somewhere or whatever, but I think that's like the computational infrastructure is, we already have that. In some scenarios in like the UP and so on, like I guess cell phone coverage is worse. But with satellite, I think that's like a solvable problem, that there is a bottom line that companies are going after for that. And I answer in that way because I think getting the capability into as many hands as possible will create that like catalyst to get more examples, get more data, train, and the system can evolve more. And then we'll have new problems like, how do you personalize to different individuals, and how do you adapt to different types of scenes?
What do you see are like the system's challenges in this use case? Like what?
Like the computer system, like efficiency or deploy the model stuff.
In this use case, so these are electric vehicles that have a limited power supply, and 4 GPUs is a lot. They don't, like the TA2 teams don't want to give us that much resources. So, the world in which there will be AI factories, like this notion, which I firmly don't believe in. I don't think generally I don't think the right way to deliver scalable AI is through larger models running on larger GPUs. I think the right way is building smaller models that run effectively on resource-constrained environments. So there are great challenges that around like, how do you distill large models into small ones? How do you optimize what model's running when, and do that effectively? And that's even in this problem, right? Like one way, when a system is in a certain state and you want to figure out, are they doing the right thing or are they doing the wrong thing? You could either run a massive model that tries to understand everything, right, and use a huge amount of power, or you can learn a representation that will do what is ultimately called like factor analysis, and each factor has its own little model associated with it, and then you're staging these models to use as few resources as possible. I think that's the way to build real systems that do this at scale. Yeah.
Well, with that, thank you, Jason. We really appreciate you. We hope to see you at other DAS lectures. If you haven't filled out the survey via the QR code, we do have paper surveys right here with pens, so please feel free. With that, thank you all for joining us tonight.
Vineyard Vines. Vineyard in Michigan. It's very expensive.
The doors closed again.
Mid me talking.
Right? It's like, come on. Yeah, like goes in that one. The other one was like a slow enough battery that it was going in and out, or it just wasn't cutting on. Yeah.
Oh, okay.
Yeah.
You're going to send.
I'm here anyways.
Yeah. So we need to like write out.
It's very limited because so that's the thing.
No, another question is for like the authorship for
What do you want to
yeah, I asked him like better. He said like I should assume like we mentioned
goes on from Jason. Jason is the last one.
I see. Yeah, Elmo's idea is like in terms of funding, like Jason is thinking about like in terms of the
I was wondering, like I didn't realize until after.
Good work. In terms of the whole sense of this paper, maybe he said like it's possible to list two equals I know I cannot understand.
What makes you want to do?
Yeah.
He just didn't mention that, so he.
Yeah. You know, if you, for example, if you were many talks right over my head. So I actually don't mind being in these ones because I'm like, oh, okay, I understand what we're talking about.
The seminar is going to be tomorrow afternoon.
Like to know something. We could. Yeah, let's do that one.
Oh, that's cool.
We don't get any.
Okay.
Nice to meet you. Nice to meet you. Thanks. We connected through doing here. Yeah.
No, I know.
Yeah.
Yeah. I even talked about the paper here. I hope you're here soon.
Yes, yeah. So I'm interested in like assessing.
I definitely appreciate our host contribution.
Yeah, I mean, we definitely are interested in working with, industry partners, but it's, like, it's different in different ways. For example, some companies are like doing